To verify a simple fact online, like your age or a bank balance, the current internet architecture requires you to hand over the underlying private data. This creates a security vulnerability. Every interaction leaves an expanding digital footprint on corporate servers, creating a centralized target for data breaches and identity theft. Blockchains like Ethereum attempted to decentralize trust by requiring every computer on the network to individually verify every single transaction. This means checking every action one by one is like an auditor verifying every single item on every customer's receipt in a global grocery store, creating a massive digital bottleneck. Both the traditional web and early blockchains share a structural flaw. They equate verification with total visibility, resulting in either a loss of privacy or crippled network speeds. There is a mathematical alternative, a way to prove a statement is true without ever seeing, transmitting, or storing the data that makes it true. In 1985, MIT researchers Shafi Goldwasser, Silvio Micali, and Charles Rackoff published a paper proposing a solution to this exact paradox. This 40-year-old mathematical framework provides the technical architecture required to resolve the privacy and scaling vulnerabilities that limit the modern web. Cryptographers use the Alibaba cave thought experiment. Alice claims she can navigate the cave's inner passage, restricted by a hidden barrier. Bob needs proof, but Alice refuses to reveal the specific method she uses. Alice enters one side of the cave, while Bob stays outside. Bob shouts for her to emerge from a specific path, A or B. If Alice has the knowledge to traverse the inner connection, she can pass through the barrier and emerge correctly every single time. If Alice were just guessing which side Bob would call, she would only be right half the time. But if Bob repeats this test 100 times and Alice is correct every instance, the probability she is guessing drops to a mathematical impossibility. Through this repetition, Bob achieves mathematical certainty that Alice possesses the restricted knowledge, even though he never learns the secret method itself. In digital systems, complex algorithms replace the physical cave. One major framework is the ZK snark, which stands for Zero Knowledge Succinct Non-Interactive Argument of Knowledge. These proofs are highly compressed and fast to verify, though they require a one-time trusted setup to generate the system's initial parameters. An alternative is the ZK Stark, or Zero Knowledge Scalable Transparent Argument of Knowledge. Starks are transparent and secure against quantum computing attacks, though they require significantly more computational power to generate. These cryptographic frameworks allow developers to translate the abstract logic of the cave into functional digital infrastructure. To make this math accessible, engineers use zero-knowledge virtual machines, or ZKVMs. A ZKVM is a computer environment that executes standard code while simultaneously generating a mathematical proof of the execution. This chart compares a standard virtual machine at the top with a ZKVM at the bottom. While both take a program and its inputs to generate an output, the ZKVM can process those inputs without ever revealing them to the host system. The output of a ZKVM is a receipt. As shown here, it splits into two parts: a public journal containing the results, and a seal, the cryptographic proof that the computation was performed correctly. This allows any software to mathematically prove it executed a specific task without ever leaking the sensitive data processed inside the program. These proofs are now moving from theory into the foundation of the decentralized internet. The most immediate application is the ZK rollup, a secondary layer that processes transactions off the main blockchain to solve the scaling bottleneck. Rollups take thousands of individual transactions and compress them into a single compact validity proof. By verifying one small proof instead of thousands of individual transfers, networks like Ethereum can reduce transaction fees while saving massive amounts of on-chain space. By offloading the computational load of verification, ZK rollups enable public ledgers to scale to billions of users while maintaining high-speed processing and low fees. Generating these mathematical proofs is computationally expensive, requiring intense processing power that can slow down standard computers. This has triggered a hardware race to build specialized silicon chips, including FPGAs and custom ASICs, designed specifically to accelerate the math behind zero-knowledge proofs. Tech giants like Google are now exploring these proofs for secure digital identity systems and password-less authentication, moving the technology into the mainstream web. The traditional internet was built on a model of administrative trust. You give a company your data and trust them to protect it. Zero-knowledge proofs establish a technical environment where truth is verified by logic alone, shifting the internet from a foundation of institutional trust to one of mathematical certainty.